Section 3.1, the derivative. What is a derivative? A derivative is a mathematical tool for studying the rate at which a quantity changes relative to another. What are some of the applications of the derivative? Number one, we're finding the slope of the tangent line to a curve. Number two, the instantaneous velocity of an object. Number three, in general, you can use the derivative to see how a change in one variable causes a change with another variable. For example, the volume of liquid in a tank with respect to time if the liquid is leaking out of a hole. Another example is cost effectiveness in construction and design. How does a derivative relate to a limit? It says, since the most basic definition of a derivative is the slope of the tangent line to a curve at any given point, let's begin with that. So it says, what is a tangent line? So let's say we have a curve that looks like this. A line tangent to the curve would be a line that's touching the curve at one specific point. So you could have lots of tangent lines. And what the derivative is going to allow us to do is find the slope of that tangent line. So it says, why might we have a problem finding the slope of a tangent line? And we know it's going to depend on where you place the line that is tangent to the function. So it all depends on where you're placing that line. Let's consider the graph of a line. If we're looking at this line right here, it's asking us, what is the slope of this line? Well, obviously, it's easy to see because this function is a linear function, and you know that the number that's in front of the x is our slope. So here our slope is 2, and it says, does the slope of the line change from when x equals 0 and when x equals 4? And we know no matter where you start on this line, the slope will never change. Now let's consider the graph of this curve, y is equal to x squared. It says, what is the slope of this curve? Well, looking at the curve, we're not going to have a slope of a line, but it's going to depend on where we draw a line that's tangent to this parabola. So depending on where the line is drawn touching the parabola, that's going to determine the slope of the line. And it says, does the slope of the line change from when x is equal to 0 to when x is equal to 4? How about x equals negative 4? And it will change, right? If we have a line that's tangent to 0, to the point at 0 right here, right on this line. And we have a point that's tangent to this line. It's going to wind up being different. So depending on where you actually draw the tangent line on the curve, touching the curve, all the slopes are going to be different. So here's our definition of the derivative. So we have a curve, and you can see that curve is in blue. If we have lines touching just the curve, we're calling that a tangent line. If we have a line going through the curve, it's going to hit at 2 points. And we learned in geometry that's called a secant line. So we can take the slope of a secant line and use this equation, that the slope of the secant line is equal to f of x sub 1 minus f of x sub 0 over x sub 1 minus x sub 0. So this is the change in the y over the change in the x's, which gives us the slope of the line. So another way that they're going to ask us for the slope of the secant line is they call it the average rate of change. So if you see the words average rate of change, they're asking for you to use this equation for the slope of the secant line. And then the slope of the tangent line, how that differs is that we're actually going to find the limit of x as x approaches x sub 0 of the change in y's over the change in x's. So f of x minus f of x sub 0 over x minus x sub 0. So we're going to say that the definition of the derivative is more commonly expressed using the h for x minus x sub 0. So the definition of the derivative becomes m tangent, or the slope of the tangent line, is equal to the limit as h approaches 0 of, and this equal sign should not be here, right? There shouldn't be any equal sign, of f of the quantity x sub 0 plus h minus f of x sub 0 over h, where h can't equal 0. So A lot of times they're not going to ask you for the derivative. What they might say is they might call this the instantaneous rate of change. So if you see the word instantaneous, you know that they're asking for you to find the derivative. If you see the average rate of change, then they're looking for the slope of the secant line. The definition of derivative is also known as the difference quotient. So what you're seeing here is called the difference quotient. So they're asking us to use the definition to find the slope of the tangent line to the parabola y is equal to x squared at the point 2, 4. And that's that blue point that you see right there. So if we drew a tangent line hitting that point, they want to know what the slope of that line is. So we're going to use slope of the tangent line is going to equal the limit as h approaches 0 of f of x sub 0 plus h minus f of x sub 0 over h. And we're going to call this first variable x sub 0, and we're going to call the 4 our f of x sub 0. So we have the slope of the tangent line is equal to the limit as h approaches 0 of f of 2 plus h minus f of 2 over h. So the slope of the tangent line is going to equal the limit as h approaches 0 of, and everywhere we see an x, we're going to substitute that into the quantity, into that x quantity. So this is going to be the quantity of 2 plus h quantity squared minus 2 squared over h. So here the slope of the tangent line is going to equal the limit as h approaches 0 of, and when we square that, that's the same thing as us saying 2 plus h times 2 plus h. So I'm going to FOIL that. So this is 4 plus 4h plus h squared minus 4 all over h. And I can simplify this. The 4's cancel. I can factor out an h, and this is 4 plus h over h. The h's cancel, and then I can use direct substitution like what I learned with my limits. So then this answer is 4. So what this tells me is that the slope of this line touching that blue point is 4. Example 2, it says find the equation of the line tangent to the curve of y is equal to 2 over x at the point 2, 1 on this curve. So you can see that 2, 1 is that gray point right there. We're looking for the line that's tangent to that point. So not only do we have to find the slope, but then eventually we have to use point slope form to find that line. So let's use our derivative to find this. So we're saying the slope of the tangent line is going to equal the limit as h approaches 0 of f of x sub 0 plus h minus f of x sub 0 over h. And remember, with the coordinate 2, 1, my x sub 0 is the first guy, and then my f of x sub 0 is the second guy. So here I have slope of the tangent line is equal to the limit as h approaches 0 of f of 2 plus h minus f of 2 over h. So the slope of the tangent line is equal to the limit as h approaches 0, and I'm going to substitute in everywhere I see an x, the 2 plus h in its spot. Minus, I have 2 over 2, and this whole thing is over h. So this winds up being 2 over 2 plus h minus 2, right, minus 2 over 2, which is going to simplify to just 1. So let's just have it subtract. Let's just subtract 1 with that, all right? And then we're going to divide that whole thing by the h. So I'm going to actually have to find a common denominator here, which I know is going to be 2 plus h. So I'm going to multiply top and bottom by 2 plus h over 2 plus h and divide it by h. So then this winds up being 2 minus 2 minus h over 2 plus h all over h. And then the 2's cancel, and I get negative h over 2 plus h all over h. And I can keep, change, flip. And when I keep, change, flip, I wind up getting that the slope of the tangent line is equal to the limit as h approaches 0 of negative h over 2 plus h times 1 over h. And this simplifies to just negative 1 over 2 plus h. Now, this is not the slope of my line. What I need to do is actually substitute in my 0 to find the actual slope. So when I do that, I get negative 2 plus 0, which is 2. So there's my slope. So now what I need to do after I do this first step is I'm going to need to use point slope form. The y minus y sub 1 is equal to m times the quantity x minus x sub 1. So I have y minus, and my y sub 1 is 1, is equal to the slope negative 1/2 times x minus 2. So I can distribute and then get y by itself. And so my final answer is going to be y is equal to negative 1/2 x, and it's going to be plus 2 once I distribute and get the y by itself. So this is the equation of the line tangent to the curve at that point, 2, 1. So let's go back to example 1, and we have y is equal to x squared, and find the instantaneous rate of change of y with respect to x at an arbitrary value of x sub 0. So whenever we see this word instantaneous, we know we're looking for the derivative or using the secant or the tangent line. So the slope of the tangent line is going to equal the limit as h approaches 0 of f of x sub 0 plus h minus f of x sub 0 over h. And whenever they say an arbitrary value, what they want us to do is take this x sub 0 and replace it with an x. So they don't want any numbers for our answers. In other words, they're looking for a formula that they can use at any point on the line that's tangent to the curve. So if we can get a formula, then we can find any slope of a line. So here we have the limit as h approaches 0 of f of x plus h minus f of x over h. So here we have the limit as h approaches 0 of x plus h quantity squared minus x squared over h. When I FOIL x plus h quantity squared, I get x squared plus 2xh plus h squared minus x squared over h. The x squareds are going to cancel, and I'm left with the limit as h approaches 0 of 2xh plus h squared over h. I'm going to factor out the h and get 2x plus h over h. The h's cancel, and then I can go to direct substitution. So the formula that's going to work for every single point that's tangent to this curve is 2x. Now my slope is not 2, so I don't want you to think that because it's a linear equation that it's going to be 2. No, it's a formula to find what the slope is. So if I'm looking for the slope of the line tangent to the point at 3, 1, then I plug in 3 for my x and I get 6. That's my slope. If I'm looking for the slope of the line tangent to the curve at negative 5, 6, then I plug in negative 5 into the x here and I get negative 10 as my slope. So let's say if we had an example like this, it says y is equal to x cubed, x sub 0 is 1, and x sub 1 is 2. So it says find the average rate of change of y in respect to x. So if we're looking for the average rate of change with y with respect to x over this interval, then they do not want us to necessarily substitute in our values just yet. So I know that average rate of change means my secant. So then that's going to equal f of x sub 1 minus f of x sub 0 over x sub 1 minus x sub 0. So that's the equation we're going to use for our average rate of change. Okay, so here, this would be, if we were using these numbers right here, right, this is the 1, 2, we would say f of x sub 1 is the 2 minus f of 1 over 2 minus 1. So then you would actually have to plug in the 2 everywhere you see an x in the equation. And then you'd plug in a 1. And then you would say 2 minus 1 is 1. And then this winds up being 8 minus 1, which is 7. It says find the instantaneous rate of change of y with respect to x at an arbitrary value of x. So whenever you see arbitrary, you know that we're just using x. There's not going to be any numbers in our answer. And whenever I see instantaneous, I know I'm looking at the derivative or the secant line. Or not the secant line, the tangent line, right? The slope of the tangent line. So this is going to be, the slope of the tangent line is equal to the limit as h approaches 0 of f of x sub 0 plus h minus f of x sub 0 over h. And we're going to plug in everywhere we see an x sub 0, the x. So this is f of x plus h minus f of x over h. So everywhere I see an x in the original problem, I'm going to plug in x plus h. So this is x plus h cubed. And then I'm going to subtract f of, I'm going to plug in, instead of f of x, I'm going to plug in x into everywhere I see an x. So then this becomes x cubed, and this whole thing is over h. So we know that x plus h quantity cubed, it means x plus h times x plus h times x plus h. So I'm going to FOIL these two, and I get x squared plus 2xh plus h squared. And then I'm going to double distribute this x plus h. So then that's going to give me x cubed plus 2x squared h plus xh squared. Now I'm going to distribute the h plus x squared h plus 2xh squared plus h cubed, and then I have minus x cubed from the other part. So I'm going to combine like terms, so I can see that this is going to match up with this, and this will match up with this. So then this is going to be x cubed plus 3x squared h plus 3xh squared plus h cubed minus x cubed over h. And the x cubes cancel. And then when I factor out my h here, I'm going to get 3x squared plus 3xh plus h squared all over h. The h's cancel. And when I go to direct substitution with my 0, I wind up getting 3x squared as my answer for the formula to find the derivative of any line tangent to a curve. Part C, it says find the instantaneous rate of change of y with respect to x at the specified value for x sub 0. So here, as soon as I see instantaneous, I know that I'm looking for the slope of the tangent line. We just found the slope of the tangent line, right, in the previous problem to equal 3x squared. So all we really need to do is take this arbitrary equation and substitute in 1 everywhere we see an x. And here we get that the slope would be 3. It says a graph of f of x and f prime of x. So we know that f of x, the original problem, was x cubed, and that's what you see in the red. Now we know that the derivative of f of x we just found to be 3x squared, and are going to be these points in blue. So the red picture is the original function, and the blue picture is the derivative function.